Hello, everyone. In this lecture, we're going to talk about classification problems, which is another example of supervised learning. Oh, I have some training data. Okay. And then I train my model H, okay, which maps from your input to some output space. This is your machine learning algorithm. Then you apply this learned model to some new data, okay, new data, and you make a prediction. Okay, T star hat, or you can call it Y, okay. So in regression problems, my target is a real number, okay? So maybe you have multiple values to predict, but you can consider them one at a time. So for each of your prediction target, it's a real number. But for classification problems, the target is a categorical variable. Okay, for example, T is in either C1, it's in the set of C1, C2, up to CK, okay? T is one of them, but T must be one of them, okay? And these categories, or the number of categories, including K, they are all predefined. Okay, so this is the definition of a classification. And the categorical variable is set only in terms of the output. It doesn't matter whether your input is a real number or it's a categorical variable, okay? It's the same as regression. You can predict the weight of an animal based on like the size of the animal or the species of the animal. It can be either categorical or continuous feature. But if it's a categorical feature, you'd rather represent it as a one-hot factor, okay? It's the same for classification. So it only says the output is a categorical variable. So one example is the spam detection, okay, based on, some features, but I'm going to introduce one of the features. It's known as bag of words features, which is very commonly used in natural language processing as a standard baseline, and also in industrial applications, it works pretty well. So the task is I want to map an email, okay? So dear someone, okay, you win $1 million, okay? So now you please contact me, and then I will ask you to give me some money, right? Some tax or some processing fee, then this is spam. And we want to represent it by a bunch of features. And in particular, the features I'm talking about here is bag of words features. You have a vocabulary V, and V is V1 up to VK, okay? So it's a k-dimensional feature, V1 up to V2 up to VK. And then if a word V1, occurs in this email, you say it's 1. If V2 does not occur in this email, you see it's 0. So for example, V1 is dear. Okay. V2 is maybe research. So, spam, you usually don't talk about research. Although there's some spam conference, okay, I don't mind. But anyway, so let's assume it's research, it does not contain research. The V3 is, dollars, okay? So you can have a binary indicator whether the word occurs or not, okay? So this is one of the feature, bag of words features with binary indicator. But you can also do the counting. For example, how many words does it occur in this email? So it's 0, but maybe dollars occur 3 times. So it's another type of the bag of words features. But the basic idea is you just consider the occurrence of the words in your vocabulary. and then you make it as a feature, okay, a feature vector. Then you would like to map it to either spam or not spam. Okay. And you only have these two choices. It cannot be in the middle. It cannot be a third category like an ad. Okay, it's not a spam, but it's not a usual email. No, it can be the number of categories, and the semantics of each category is predetermined. So this is the example of spam. Another example, maybe digit recognition. Okay, I have a bunch of, I have an image and it's represented by a bunch of pixels. Okay, and I want to model it as a, the digit is indeed 1 among, all you have for one digit is 0, 1, up to 9, okay? It's one of these category. And then I also know that this image must have one digit in that, then it's one of them. So this is the digit recognition task. And it's also a classic classification task. Okay. And here, even if I say the target is 0, 1, up to 9, they are not numerical numbers. They're not saying my feature or my value for 0 is none, okay? I have no value for that variable, but I have 1, but I have 2, which is twice as much as 1. No, this is not the numerical number. This is not the value. This is the category that conceptually we humans recognize it as 1. But in some other language, in English, we don't call it 1 as the vertical bar. We say it's O and E, right? So this is the conceptual 1 that we have in our mind. It's not the number. So it's a classification task. Okay. So the third example is I would like to predict how user like a product on some e-commerce website. Okay, so this is the e-commerce. Like prediction, or the rating prediction. Okay, so I have a product. So I have some product. And then the rating could be either 5-star. So I'm not predicting the average rating, but I'm just predicting what is the most likely rating, and it must be a whole number. Okay, 4-star, or 3-star, 2-star, or 1-star. Okay. So is it a regression problem or is it a classification problem? So it turns out that it can be either modeled as a regression problem, or it can be modeled as a classification problem, right? It's 1, 2, 3, 4, 5. So if you model the regression problem, you are making use of the order information among the ratings, okay? I know 2 is better than 1, and 3 is better than 2, and 4 is better than 3, and 5 is better than 4, right? So you have the order information. And the other thing is you have the distance information, While 3 is better than 2 and also better than 1, the gap between 3 and 2 is half of the gap of 3 and 1, okay? So this is the distance information, or the Euclidean metric intrinsic to the real space. You are making use of that. So if you see some feature and W transpose X, you predict it as your target. So if a feature is twice as much as before, then the weight, this feature contributes twice for the target, right? And the pros now becomes the cons for classification. So there's no order information. So even if you say this is the 5th category, 4th category, so and so forth, And this is the first category. And I can shuffle all the categories. This is my first category, second category, third category, fourth, and fifth. There's no difference, okay? So no order information and no useful distance information, right? The distance between two categories is ij is, by the discrete metric itself, the distance is 1 if j is not, I is not j, 0 if I is j. It basically says, okay, the first category, the one category is the same as itself, but it's different from other categories. You have no useful distance information. Okay. But then the cons for regression, it becomes less flexible. Like suppose you have a linear regression model target. Okay, it's a linear regression model plus some bias. Okay, then it's not flexible in determining what does it mean by rating 4 and rating 3. Okay, it must fit this line, and then you can round it to 5 and 3, 5, 4, 3. Okay, but this must be a linear, right? This must be a linear line. But maybe our human ratings are different. Maybe we are very happy, okay? We are very sensitive to the high ratings, but we are insensitive to the low ratings. That we cannot do it by a linear model, or given a particular model, we cannot easily adjust such information. But if you model it as a classification problem, then it becomes more flexible, okay? As you can learn the semantics of each category individually. Okay. Okay. So it turns out that a particular task can either be modeled as a regression problem or a classification problem. And the rule of the thumb to choose between different models or choose between different hyperparameters or different variants or different settings is always by validation. Okay. So give a particular data set, give a particular task, and I can try both. And then I will notice which is the better model for this task, okay? And my intuition is if you have, many samples, probably classification is better. But if you have fewer samples, like a few hundred samples, maybe you need to do the regression. You can pull the information all together, right? But if you learn the classification, then you are learning the semantics of each category individually. Okay, here are a few examples of the classification tasks. And a few terminology issues. If your target has two values, target has two values, this is known as the binary classification. And if your target has multiple values or multiple candidate values, you have, it's known as the multi-class classification. But I feel reluctant to say whether binary classification is a special case of multi-class classification. You can say that. I mean, if you have two classes, it's not much different from you have three classes, right? So I will not say binary classification is completely different from multi-class classification, but we will make a comparison that there's another classification called multi-label classification. When we talk about multi-class classification, we mean that the target must be one of the values in your candidate target, okay, in your candidate categories. But in multi-label classification, your target could be a few labels in your predefined set, okay? So here, if we talk about multi-class classification, then It must be one hot. The target must be one hot, one and only one in the candidate set. Okay. And binary classification, I would say it's a special case of multi-class classification where the target is 2. But multi-label says T, now T is a set, okay, is a subset as category 1, category 2, up to category K. It's still predefined, but it now becomes a subset. But of course, it can also be represented as a vector. I say T is 0 and 1 up to, to the power of K, if one element is on, then it says this label is on, but if one element is 0, then it says this label is 0, okay? And the example is maybe emotion classification. Okay, so I have a text. I have some text. And I want to detect the emotion of the text. And the candidate labels is maybe happy, or maybe joy, or maybe sad, or maybe angry, or maybe something else. So in this case, for a particular piece of text, it can be both sad and angry, okay? But it's not happy, not here, not here. So in this case, it's a multi-label. You have 2 labels, sad and angry, okay? So it's a multi-class classification. And it's similar to like tagging an emoji for a particular text. You can tag multiple appropriate emojis for that. Then it's a multi-label classification. Another example is image classification. Okay. So here is an image of maybe the Rocky Mountains. So I have some creek, and I have some, mountains, and I have the sun. Okay. So what are the candidate labels? The candidate labels may be mountain, creek, sun, or maybe you have house or car, or maybe book, so on and so forth. Suppose you have finite number of categories, okay? And in this case, it's possible that your ground truth, your target in your training data contains mountain tags, contains the tags of mountain, creek, and sun for this image, but not other things. Okay, then it's a multi-label classification. In this case, it's a multi-label classification. But it's also possible that your classification task is asking what is the major object in the image, okay? Or the main theme of this image, okay? Then the main theme here is the mountain, right? So you only have mountain. The main theme is not creek. If it's a creek, then the image will be here. It's not a sun because the main theme is it's a sun, then the image will be like this, right? So if your target only says it's mountain, it's creek, it's not creek, it's not sun, not here, not here, then again, it becomes a multi-class classification, okay? So there are different tasks. And obviously, multi-class is simpler because you only have to classify one. Okay. And this will be the main focus of this course. What if you have multi-label? So if you have multi-label, the easiest approach is you break it down into multiple binary classifications. You ask if mountain occurs or not in this image, and then you ask if creek occurs or not in this image, so on and so forth. After you solve each of the binary classification problem, you solve the multi-label classification problem. So this is the simplest approach. But more advanced approach is modeling the relationship among different labels. For example, mountain and creek are more likely to co-occur, but it's less likely to co-occur with book, okay? So you are modeling the relationship among the labels, then it's more advanced. But as a starting point, you can just treat the multi-label classification as multiple small binary classifications. Okay. In this course, we mainly focus on multi-class classification. Okay, I guess it's clear for the task formulation of classification. Next, we are going to talk about the measure of success. Okay, how can I measure whether a model is successful or not? The most commonly used metric is the accuracy or the error. They are the same thing, right? So 1 minus error is the accuracy. So let's talk about accuracy. It looks better. You know, it looks we're more optimistic. So the accuracy models how many correct predictions among total number of samples, okay? So this is the accuracy, just means how much you are correct. And it works well for many tasks. If you make an error, then your accuracy is lower. If you make more errors, then your accuracy is lower and lower, okay? But here is a severe problem for accuracy, which is known as the skewed class classification. Let's think of binary case. We only have 2 labels, 0 and 1, okay? Suppose 99% of my samples is 0 and 1% of my samples is 1. Okay. It's possible. For example, this is cancer. We know most humans do not have cancers. So most of us are healthy, but a few of us unluckily have cancer. Then if we want to predict whether we have a cancer or not, you know, for example, based on the X-ray of our lung radiology, like this. Okay. Now this time, if we use the accuracy, it's not a very good measure of success because I can have a very trivial machine learning system. I say, everyone is good, everyone is happy. A trivial machine learning model, that's everyone is good. Then the accuracy becomes 99%, right? So most of the humans do not have cancers, and I predict none of us have cancers. But there's 1% of humans who unlikely have the cancer, then I don't make a prediction, I still get 99% accuracy. So no good. So this shows that accuracy is not a very good measure of success for skewed class classification because machine learning model can easily fool the metric or cheat the metric. Basically, it says I don't have to do anything serious. I can achieve a very high score. If I want to model the remaining, like a small percent of my samples, it may hurt my performance on the majority class, and the performance may be even worse than 99%. Right? And also because you have different consequences. For false positive and false negative. So the meaning for false positive means I predict the person has cancer, and in fact, the patient does not have cancer. False negative says I predict the patient does not have the cancer, but actually the patient has the cancer. So you see the consequences are very different. So if I don't have a cancer, and I'm predicted diagnosed by a cancer by the X-ray, it's not a problem. I may do a further investigation like fMRI, or maybe I just do some surgery and get some tissues out, and then we see it's not a cancer. Okay, I'm very happy. So the false positive, you have a low risk if you make a false positive error. But if you have a false negative error, I have a cancer, I should have been diagnosed based on this X-ray, but unfortunately, the machine learning model makes a false negative error. And then I feel I'm healthy, okay? Then I miss the chance for the early diagnosis. And after a few months, maybe the cancer may be developed to late stages, and then, it cannot be very well treated. So in this case, you have a high risk if you make a false negative error. To solve this problem, I would suggest you have a confusion matrix. Confusion matrix is a two-dimensional matrix where you have one axis predicted positive and negative. Okay? And the other axis, whether the patient is actually positive or negative. Okay. Then you count the number here, okay? You count how many patients are actually positive and predicted positive. How many patients are actually positive but predicted negative, so on and so forth. And then you can fill in the numbers like I have 90 patients here, 5 patients here, 4 patients here, and 1 patient here. Okay. Suppose now I know that if you have a false positive, your risk is 1 unit. But if you have a false negative, your risk is 10 units, okay? Then I can assign the weights for them, okay? So this is negative, so this is false negative. This is positive, is false positive, okay? Then the weighted risk, you can say the weighted risk for this confusion matrix is 1 times 1 plus, this is false negative, so it should be 10 times 1 plus 4 times 1, right? So the unit is by 10, here is 1, okay? The risk, the loss is 10 times more for false negative than false positive, then the weighted risk is 14, okay? You can normalize by 100, but you can also ignore the normalization, it doesn't matter. But what if the other way around, I have the 1 patient with false positive and 4 patients false negative, then this time the weighted risk is 10 times 4 plus 1 times 1, okay? So this gives me 41, okay? And obviously you see making a false negative error is more severe than false positive error, okay? So the idea of weighted risk, it really complies to the utility theory or some decision theory. You want to maximize your expected utility, or you want to minimize your expected risk, okay? But the issue is, if I do things like this, the difficulty is the weights are highly subjective. Okay, so why not, I say it's 9, it's not 10, or maybe it's 11. So the weights are highly subjective, and it's actually very difficult to convince the reviewer that this is a good weight. Okay, it's very hard to do that. To mitigate this problem, I would suggest we're going to use the precision recall and F scores. Okay, there are more robust metrics that cannot be easily cheated, and they don't involve too many subjective weights. Okay. So the definition for precision is how much you predicted positive. So predicted positive, okay, the set that you predicted positive intersect, so I can call it M, okay? Intersect, it's actually positive, okay? Divided by how much you predict positive, okay? And I take the size of the set, okay? So precision basically just means among the samples that you predicted positive, what is the accuracy, okay? And the recall is similar, but you have a different denominator. You still have the intersection between predictive positive and actually positive, but you divide it by the number of samples that are actually positive. Okay. It basically says among all the positive samples, how many of them you recover, okay? It's recall, you recall it, right? So going back to the confusion matrix, the precision is this number divided by predicted positive. So where's the predicted positive? The predicted positive is this column, right? So it's predicted positive, then it's 5 plus 1. So regarding this confusion matrix, the precision is 5 divided by 6. And what is the recall? Recall, I can change another color. It's still this number, but it's divided by actual positive. So it's actual positive. So this number divided by this row, then it's 9, okay? 5 divided by 9. So this is a recall. And when you combine them together, you get a F measure or the F score. Okay, the F score is computed by F is 2PR divided by P plus R. It's the harmonic mean between the precision and recall. And it can be weighted, the importance of the precision and recall can be weighted by hyperparameter beta, which is beta square, 1 plus beta square PR divided by beta square P plus R, okay? So the beta gives you a weight between P and R, whether precision is more important than recall or recall is more important than precision, okay? But in this case, the value for beta is also subjective. It's very hard to determine or convince the reviewer that this is the correct beta for the task. So that's why we typically just have F1, okay? If you plug beta as 1, then you get this score, okay? So F1 is more commonly used for skewed classification. The metric cannot be easily cheated. You can try it yourself. Like, suppose you have 99 of them are healthy, but 1% of them have the cancer. Now, if you predict all of them as healthy, then you get recall of 0, then you take the harmonic mean, then you get 0. The F score is 0. With the F score, your machine learning model cannot easily fool the metric, and the metric has a very wide range of sensitive regions, okay? The metric is not inflated to like 99% to 100. The range is really small, but now you have a wider range that your metric is effective, okay? And just a caveat, when we talk about precision and recall, we typically talk about the positive or the negative category, but the positive category must be a minority. The minority category, okay? It just means it must be a small portion of my data are positive. If your majority samples are positive, then you cannot use the F score like this. You need to swap the positive and negative labels, okay? Otherwise, we have a written assignment. You will see that the F-score is not inflated to a very narrow region, and for whatever models you have, it just gives you decent results, but actually the metric, it becomes deficient. Okay. This is the evaluation metric. Then the hypothesis class. Okay, let's talk about binary classification first, because it's the simplest model. So for hypothesis class, we first think of the linear hypothesis class, linear classification. Again, it's because of simplicity. If we understand the linear model well, we can extend the model to the nonlinear space by either nonlinear features or by nonlinear kernels or by learnable nonlinear functions. So hypothesis class for linear classification is not. So it's not your target, predicted target is some W transpose X plus D. We typically make the bias more explicit in the classification case. Okay, it's not this case. Because the target must be some either 0 or 1. Okay, the target hat must be 0 and 1. So it's not actually, it's actually not saying your hypothesis itself, it's a linear function. So it's a linear function, no. The hypothesis should be a step function saying, if your feature, the goodness is greater than or equal to 0 or some number, but you can absorb the number into B, okay? So I just say 0. So if I say this is a goodness, which is a linear function of your input, if the goodness is greater than or equal to 0, then I say I predict 1. If my goodness is less than or equal to 0, I don't mind 0 because the chance of getting exactly 0 is very small, but I just say if it's less than 0, then I predict 0, okay? So this shows the hypothesis is actually a step function of whether your goodness exceeds a particular value. This is the linear classification. So I can compactly represent it by an indicator function, W transpose X plus B is greater than or equal to 0. So this one is the indicator function. It gives you 1 if the condition is satisfied or 0 if the condition is not satisfied. Okay. So one-dimensional case. So my X is one-dimensional, Then the goodness is W X plus B is greater than or equal to 0, right? Then suppose W is not 0, then X is greater than or equal to minus B divided by 0, but I can rebrand this as a threshold T. So the linear classification for a one-dimensional case is just a thresholding, okay? So I say threshold. If it's greater than or equal to this part, I predict 1. If less than or this point, I predict 0, okay? So this is my hypothesis, one of my hypothesis function, okay? One of the hypotheses. It can also be the other way around, right? So if your W becomes the negative of your previous W, then you say, if it's less than this part, it's 1, okay? If it's greater than this part, it's 0, okay? So this is my hypothesis function. It's a step function that if the goodness exceeds something, you say good. If it doesn't exceed the threshold, you say no good, okay? And this point, we call it decision boundary, or sometimes called decision surface, okay? Basically, it says, if you cross the boundary, then I'll make a different prediction. In the two-dimensional case, suppose my X1 and X2 in the two-dimensional case, suppose I have x1 and x2, and suppose this is my decision boundary, okay? So for linear classification, I just mean the decision boundary is linear. So this line can be represented by W transpose X plus B equals 0 with W not a zero vector. Okay, so this is my decision boundary. Then, perpendicular to this decision boundary, you have a vector. It's either pointing here or pointing there. This is known as the normal vector of the hyperplane or the decision boundary, which is W. Okay, so the W vector is known as the normal vector, which will be perpendicular to your decision boundary. It points out to the category that you will predict 1. Okay, this is your prediction 1. This is your prediction 0. Okay, so this is the two-dimensional case. And if you want to make your hypothesis more explicitly, you can say, this is my x1, x2 space, okay? And this is my decision boundary. So this line is just this line. And my prediction is t hat, okay? So it's either 0 or 1, right? Then I have a step function. You see, you have a step function. Okay. So this step function is indeed a stair, right? So the step function is my hypothesis, right? The goodness increases in the normal vector of W, okay? So if you go in this direction in the x1, x2 space, okay? So I guess the normal vector, when you have a projection, you should have a direction somewhere here, okay? So if you go in this way, then your goodness increases. If you go in opposite way, your goodness decreases. If you cross the decision boundary, I will predict 1. If you haven't crossed the decision boundary or you are in the lower half of the space, I predict 0. Okay. So the H surface is my hypothesis function, but the decision boundary is not your hypothesis function. It's where you make change in your hypothesis function. Okay. 3D dimensional case. Now things becomes trickier. So again, the decision boundary is a hyperplane. Okay, so maybe some of your samples are here, so one category. Some of your samples are there. There are another category. Okay, so you think of a 3-dimensional case. Then maybe your decision boundary would be a 2-dimensional plane like this. Then it's a pretty good classifier for this data set, right? You perfectly separate the blue samples and the orange samples, okay? And suppose the blue samples are 1s and the orange samples are 0s, then your normal vector should point to this half space, okay? So this is the decision boundary, which is also denoted by W transpose X plus B, okay? This is the normal vector W. So that's why we typically, in classification, we don't use the extended features, okay? In linear regression, if you extend it by a trivial feature, it's more convenient. But in classification, we typically talk about the decision boundary, then we don't use the extended feature. And we typically don't draw the hypothesis function because it gives you no information. All the information is self-clear in the decision boundary. So that's why we typically draw things like this, 0 and 1, okay? Or a hyperplane like this. So this is the 3-dimensional case. If it's a higher dimensional case, then I told you how to think of a high dimensional space. You just draw it in 3-dimensional and say it's high dimensional, it's 300 dimensional. Now things become 300 dimensional. It's not very different from this case, okay? So this is the hypothesis class. We're going to work for the binary classification first, and then we think of the linear classification where my decision boundary is a linear line or linear hyperplane, and then it's given by a linear equation. It fully specifies my decision boundary. And then the hypothesis is a step function based on my decision boundary. finally, a few heuristics for doing classification. Okay, we also talk about binary classification because it's simpler. A few. Okay, my first attempt is linear regression model for classification. So the idea is in classification, my target in the binary classification is either 0 or 1, right? So it's either 0 or 1. But we know 0 and 1 are a subset of my real number. Okay. So this shows that if you apply a linear regression model to classification, the algorithm still works. You will not have any runtime error because the classification label is actually a subset of your real number. Okay, so it still works. But whether it will give you good performance or not, it's still questionable. Suppose I'm doing one-dimensional case. So these are my, okay, why not, let's say my negative samples are orange circle, and my positive samples are blue plus, okay? So plus looks like positive or 1. So here's 1, Then I can learn a linear regression model. So this is my target, right? Or maybe the target is not necessarily centered anyway. Then I can learn a linear regression model like this, okay? And I cut off by 0.5, right? The target here is 1, it's 0, so I can cut it off by 0.5, okay? If I cut it off by 0.5, then I get a step function saying, okay, this time my step function is drawn in purple. I'm saying, this is my learned hypothesis. Does it work? Programming-wise, it works, but the performance will not be very good because maybe you have outliers, So maybe you have some outliers here, okay? So here you still have a few positive samples. This time, these samples differ from your predicted value too much, okay? Because they're still 1, but your predicted values goes up very quickly. And then you are bending the learned linear regression line to this flat region, okay? To this flat region. Now, if you cut it off by 0.5, then you get a few samples wrong, okay? And this can be very severe if you have a few more samples, then the slope will be smaller and smaller. And then, if you still cut it off here, then you will have more and more samples predicted wrong, right? So linear regression for classification is something that can work out, but it's no good, okay? Not good. And the reason is for these samples, okay? For these samples, you predict it very correctly, right? It has a very high goodness, it's very good, but you have a large penalty for that. So for the samples that you predict very correctly, you have a very large penalty and try to make it close to 1. So that is a bad idea. So a treatment will be, I will squash my linear line like this to some, function like this, okay? And it will saturate if it's very good or it's very bad. Then in this case, you don't have a large penalty here, okay? All the samples are well predicted, so you have learned a very good model. But what if one of your samples are here? Then, the squash function, I think I should draw it darker. The squash function is here, okay? But now you predict this sample wrong, and you can learn from the wrongly predicted samples. If you predict a sample very well with high confidence, then you don't have to learn from that. The loss of that sample is not important. You should ignore that loss. So that's why you need to squash the linear line a little bit. Okay, the line, the affine line a little bit for your classification. So this is the first attempt. Linear regression for classification is not a good idea, but it can be salvaged by some squashing functions, which we'll discuss later. The second attempt is, suppose I have a two-dimensional space. I have a few samples like these. And I have another few samples like these. Okay. So Fisher, who is a statistician in the early last century, he thought if you want to have a good classifier, you should find so suppose this is your classifier, then you can project your data into the line perpendicular to that decision boundary, and you can model the variance of different categories, right? So the variance here is the in-class variance. Okay. And you can also model the variance about different categories. Okay, so the difference here, maybe you take the square, is the between class variance. Okay, so Fisher says, if I have a good decision boundary, then I should maximize the between class variance. Okay, I should make my classes as distinguishable as possible. Then if you project it to some lower dimensional space, and you compute the variance of your projection, you compute the variance of your samples within a class, it should be as small as possible. Right? So compared with another decision boundary, so compared with another decision boundary, maybe this. So this is my decision boundary here. Okay, then when you project data onto this line, you have a blue class like this, and you have a red class like this. Okay, so you see the in-class variance is very large. Okay, the in-class variance is very large, but the between-class variance is smaller than that. Okay, so these quantities are very well defined, but we're not going to touch this in this course. But if you work it out, it gives you some optimization problem, and this is known as the Fisher's linear discriminant. By discriminant, we just mean that it's not a probability model. So I have some heuristic objective. I just optimize this objective, and it gives me a meaningful classifier. Okay. So this idea is by Fisher's. Okay. The third attempt is another very well-known classifier, is the max margin. Okay. So you see, if your model is good, if your decision boundary is good, the data sample are far away from your decision boundary. You see, this region is very large, so I call it a margin. This is true margin. If your sample is not good, just like in this case, I don't have this. Okay, max margin does not have the variance stuff. Okay, if your decision boundary is not good, like in this case, the margin, the data is very close to your margin, right? Even one sample is on your margin, on your decision boundary. So the margin is really narrow. Okay, so why not, let's say my classification, my training principle is to maximize the margin of your data. Okay. So this is known as the support vector machine. The points on the margin are my support vectors. And we'll talk about the optimization of support vector machines in future lectures. But here is just the first intuition that why support vector machine works. So what are the other heuristics for solving the linear classification problems? But in the next few lectures, I'm going to present probabilistic modeling for linear classification. Thanks, see you next time.